Alrighty. Welcome to another session here, and I guess let's learn Linux. Today's going to be a big one. I'm going to try and do as much of Chapter 10, kernel synchronization methods, as I can. Hopefully, we get to a coding exercise to just see how some of the synchronization I guess API or primitives, whatever you call it, works. And hopefully, we all come out of it having a better understanding of how the kernel does basic synchronization for concurrent scenarios. Okay, let's begin. So, the previous chapter discussed the sources of and solutions to race conditions. Thankfully, the Linux kernel provides a family of synchronization methods. The Linux kernel synchronization methods enable developers to write efficient and race-free code. This chapter discusses these methods and their interfaces, behavior, and use. Atomic operations. We start our discussion of synchronization methods with atomic operations because they are the foundation on which other synchronization methods are built. Okay, atomic operations. So these are operations that the CPU can do in one shot, one instruction, pretty much. Atomic operations provide instructions that execute atomically without interruption. Just as the atom was originally thought to be an indivisible particle, so they thought. Atomic operations are indivisible instructions. For example, as discussed in the previous chapter, an atomic increment can read and increment a variable by one in a single indivisible and uninterruptible step. So that's the important part. An atomic operation is uninterruptible, meaning in any moment as a thread, for example, is trying to execute some sort of instruction, if it's uninterruptible, it will be able to finish that operation without any concerns of being preempted. And we know that the term preempted here means that it gets kicked off from being running into some sort of ready queue, and another thread comes in and takes over running their own things too, potentially operating on the same shared data. So it's important to understand that atomic also means uninterruptible too, in conjunction with indivisible. Okay. Recall this simple race in incrementing an integer that we discussed in the previous chapter. So then here, thread 1, we have get I, which is going to be 7. Thread 2 also gets I, which is 7. Okay, so now at this point, thread 1 increments I. So this is not atomic, right? This is just a normal operation, like a normal instruction where we just want to increment I. So we increment I, we go from 7 to 8. Okay, but on thread 2's end, once thread 1 gets preempted right after that, you see this part here, they get preempted, thread 2 actually becomes active again. And since its I, from the very beginning, it got was 7 in its own stack, right? Because we have int I equals get I or something like that. That would have assigned the I to be 7 on that stack. Thread 2 gets its own stack, just to reiterate. It'll increment I to 8. Okay, now both of them, thread 1 and thread 2, have both incremented I, and now they're both 8. So then thread 2 gets preempted, and then thread 1 becomes awake again and writes 8 back to I in memory, because at that point it had been operating on its local variable, its stack variable, right? But now it's writing back to memory, or not variable, register, sorry. Register, not stack, so register. And so now it gets preempted, okay? And then thread 2 writes its register value back into memory, in this case, to store I. So I is the shared value in this case. I know I messed up. I should have said register, not stack. Just so remember, threads also get their own set of like register, like a view of the registers too, in this case. Okay. With atomic operators, this race does not indeed cannot occur. So if we change this to atomic operations, there's no such way this can happen, the scenario that we had talked about earlier above. So it cannot occur. Instead, the outcome is always one of the following. So thread 1 gets, increments, and stores I all in one instruction. Same thing for thread 2. So we go from 8 in thread 1, thread 2 gets 9. The reason why thread 2 can't execute anything here at the same time is because since it's atomic operation, the CPU will physically not allow thread 2 to even touch I because thread 1 already has it. So the other scenario is that if thread 2 had beaten thread 1 to the punch, thread 2 could have gotten I when it was 7 and then incremented to 8. Now thread 1 could have been active concurrently with maybe on another CPU core, so it's allowed to execute at the same time. It could not have gotten I at all because since it's atomic, it physically cannot get that I. So then by the time thread 2 is done, it will actually be able to now increment I, which is now 8 because of thread 2's operation on I from 7 to 8 to 9 in this case. So the ultimate value, always 9, is correct. It is never possible for the two operations to occur on the same variable concurrently. So let's reiterate that. It is never possible for the two atomic operations to occur on the same variable concurrently. Therefore, it is not possible for the increments to race. The kernel provides two sets of interfaces for atomic operations, one that operates on integers and another that operates on individual bits. These interfaces are implemented on every architecture that Linux supports. Okay, so the APIs and all the data types and structures that exist in Linux to handle the atomic operations, okay, with integers and individual bits are already implemented in every single CPU architecture that Linux supports. So this includes x86, ARM, Spark, whatever. So they're there. So we don't have to worry specifically about the CPU architecture, how to actually do this stuff. We have the high-level APIs provided by the kernel code in order for us to actually get it done. So it doesn't matter what architecture you're actually programming in, the Linux kernel code will provide it. Again, that's how I interpreted it. So most architectures contain instructions that provide atomic versions of simple arithmetic operations. Other architectures lacking direct atomic operations provide an operation to lock the memory bus for a single operation, thus guaranteeing that another memory affecting operation cannot occur simultaneously. There's differences in how architectures can do this, right? Just like what the book said. So that's the reason why Linux provides the abstraction necessary to do this. So you don't have to care exactly, do I lock the memory bus or do I do this other operation in order to get something atomic? So anyway, atomic integer operations. The atomic integer methods operate on a special data type, atomic T. So this is a data type. This special type is used as opposed to having the functions work directly on the C int type. So underneath the hood, it's probably just an int, this atomic T thing. So for several reasons. First, having the atomic functions accept only the atomic T type ensures that the atomic operations are used only with these special types. Okay, so that locks it down from you abusing atomic operations on non-atomic T type things. Okay, the compiler will scream at you. It won't even run, I guess. Likewise, it also ensures that the data types are not passed to any non-atomic functions. Indeed, what good would atomic operations be if they were not consistently used on the data? Next, the use of atomic T ensures that the compiler does not erroneously but cleverly optimize access to that value. So yeah, you know how in C you can compile your program with different optimizations? When you do that in C with the compiler can end up inadvertently rearrange or rewrite some instructions because it's more performant. And so when you do this, it can actually ruin some of the data access patterns that you deliberately put into your code and mess everything up with weird bugs. So with Atomic T, it's kind of just ensuring that the compiler doesn't fiddle around with it during the compilation process. So it's very important that that stays intact, and with any sort of optimization, it's instructions or code that involves the Atomic T type doesn't get inadvertently rearranged or rewritten. Anyway, it is important that the atomic operations receive the correct memory address and not an alias. Finally, use of Atomic T can hide any architecture-specific differences in its implementation. The Atomic T type is defined in Linux/types.h. So this is the atomic type here. Oh, so it's not an integer. It's a struct that contains an integer called counter. Okay. So it's volatile. So that's telling the compiler that this is going to be changing. I think volatile means to like make sure that this stays in like a register or something like that for speed. And it won't get optimized out where instructions put that into memory. So it always stays in some register. I could be wrong. Actually, let's just check. Volatile. C. Volatile. Okay, so what does it mean? The proper use of C's volatile keyword is poorly understood by many programmers. Uh-oh, that might be me. This is not surprising, as most C texts dismiss volatile in a sentence or two. This article will teach you the proper way to use volatile. Okay. Have you experienced any of the following in your C or C++ embedded code? Code that works fine until you enable compiler optimizations. Code that works fine until interrupts are enabled. Flaky hardware drivers. Or RTOS tasks that work fine in isolation until other tasks spawn. Yes, if you answer to any of those above, it's likely you didn't use the C keyword volatile. You are not alone. The use of volatile is poorly understood by too many programmers. Okay. Let's see. Okay, here we go. So C's volatile keyword is a qualifier that is applied to a variable when it is declared. It tells the compiler that the value of a variable may change at any time without any action being taken by the code the compiler finds nearby. So we were there. We were kind of right. The implications of this can be quite serious, and sometimes software experts testify in regard to product failures. So if you don't know this fact, then you can write really buggy software. Okay. So why does this work? Let's see. Okay, so to declare a variable volatile, include the keyword volatile before or after the data type in the variable definition. For instance, both of these declarations will declare an unsigned 16-bit integer value to be a volatile integer. Okay. It turns out that pointers to volatile variables are very common, especially with memory mapped I/O registers. Both of these declarations declare preg to be a pointer to a volatile unsigned 8-bit integer. Okay, volatile pointers. Okay, so yeah, sure. Here, let's just do this one. Proper use of C's volatile keywords. A variable should be declared volatile whenever its value could change unexpectedly. That makes sense. That links back to why this one has to be volatile, because you can have many like threads concurrently accessing it, and that can cause a lot of issues. It's noisy. So memory map peripheral registers, global variables modified by an interrupt service routine, and global variables accessed by multiple tasks within the multi-threaded application. Okay, good enough for me. We know that volatile is a hint to the compiler that this variable could change, and it's used if it's probably going to be accessed by a lot of things. There we go. Good enough for us for now. Okay. Despite being an integer and thus 32 bits on all the machines that Linux... Oops. What am I doing? Okay. Despite being an integer and thus 32 bits on all the machines that Linux supports, Developers and their code once had to assume that an atomic T was no larger than 24 bits in size. What? Oh, okay. Oh, okay. The Spark port in Linux has an odd implementation of atomic operations. A lock was embedded in the lower 8 bits of the 32-bit int. The lock was used to protect concurrent access to the atomic type because the Spark architecture lacks appropriate support at the instruction level. Okay. All right. So, because Spark, okay, so you have many CPU architectures in the world, but Spark decided to not have instruction level support for atomic operations. Therefore, like a workaround was made so that the lower 8 bits of this 32-bit integer was used like a lock. So that's why most people assume that this would be 24 bits even though it's a 32-bit integer, because Spark, you had to take care of the Spark situation. Okay. So I don't think that's an important detail, no, but it's just confusing to read. Although code that assumed that the full 32-bit range existed would work on other machines, it would have failed in strange and subtle ways on Spark machines. And that is just rude. Indeed. Recently, clever hacks have allowed Spark to provide a fully usable 32-bit atomic T. And this limitation is no more. Okay, good. So we don't have to worry about it anymore. Just think of it as a 32-bit int and call it a day. I don't know why this... Okay, whatever. So if this is the 32-bit integer, then the 8-bit lock would be here, and then your integer would be here, your true counter would be here. So the declarations needed to use atomic integer operations are in ASM atomic.h. Some architectures provide additional methods that are unique to that architecture, but all architectures provide at least a minimum set of operations that are used throughout the kernel. When you write kernel code, you can ensure that these operations are correctly implemented on all architectures. Defining an atomic T is done in the usual manner. Optionally, you can set it to an initial value. So it's just like declaring any variable, right? So we have the type and we have the label. So atomic T V. So you defined or you declared V in this case. Or you can declare and define with this macro here called atomic init with 0 as initial value. And all this will start to make sense soon. So atomic TU equals atomic init 0. So we define, or I like to say declare U and define it to be 0. Initialize too, I guess. Same thing. So operations are all simple. So yeah, so with these atomic T values, you can actually do various things to it with API, right? So let's say you wanted to set now, like you declared atomic T to be atomic T with the label V. And now you want to set it to 4, the value 4. So then you can do atomic underscore set with the pointer to the atomic T. Given, like, so you take the address, right, and you turn that into a pointer. So a pointer to atomic T with the value 4. Or you want to add 2 to whatever is in the value pointed by V right here. Okay? Or you want to just increment. And I think this is probably the most common one. So atomic inc with the pointer to V. So the atomic T V. Okay? So, and also, if you ever need to convert an atomic T to an int, we can use atomic read. So that's how we actually get the value inside the atomic T. So atomic read with the pointer to the atomic T V will actually get you back the integer version value, which is safe to just be formatted as %d, no warnings whatsoever, I guess, with 7 in this case. So, okay, cool. Basic API, right? A common, so then okay, let me just put more detail in that. It's basic API, and you use this so that you can actually ensure that if you have some sort of integer that you're incrementing or whatever to keep track of something, to like maybe like a lock, right, that it is all done in one operation. So like this atomic add here will effectively add 2 to the atomic T pointed by or the value pointed by atomic TV, right? in an indivisible manner, right? In an indivisible and uninterruptible manner. It'll add 2 to whatever's in V here in an uninterruptible and indivisible manner. So that's how you can ensure that 2 gets added without like having being preempted and getting corrupted if, something were to happen. So the yeah. So a common use of the atomic integer operations is implement counters. Protecting a sole counter with a complex locking scheme is overkill. So instead, developers use atomic ink and the atomic deck, which are much lighter in weight. So these are good helpers to just increment and decrement. Another use of atomic integer operations is atomically performing an operation and testing the result. A common example is the atomic decrement and test. So you basically have this API here called atomic dec and test that takes in a pointer to atomic T called V, and it's just going to decrement the value and then or first I think it decrements the value and then tests it, and then if it couldn't decrement because it was like locked or something like that, then I think you automatically, or the thread that's calling it will sleep or something like this. So let's see. This function decrements by one the given atomic value. Okay, if the result is 0, it returns true. Otherwise, it returns false. Okay, a full listing of the standard atomic integer operations, those found in all architectures, in table 10.1. All operations implemented on a specific architecture can be found in ASM atomic H. Oh, okay. So it just returns a value then. If you were able to decrement it and get it down to 0, then this will return true, and otherwise returns false. Okay, more reasons on that, I guess, soon. Okay, so this is like the full API. I don't know. I don't want to read all of them, but basically if you have an add, of course you have a subtract. You have an increment, of course you have a decrement. You have a sub and test, of course you have an add and test somewhere. But yeah, add and sub, right? Add and sub are just given the values with the atomic T pointer, right? And then you have dec and increment and test too. So yeah, let's keep going. So the atomic operations are typically implemented as inline functions with inline assembly. In the case of where a specific function is inherently atomic, okay, the given function is usually just a macro. In the case where a specific function is inherently atomic, the given function is usually just a macro. So these are just macros. For example, on most architectures, a word size read is always atomic. That is a read of a single word, meaning if you have a 64-bit system, 64 bits, cannot complete in the middle of a write to that word. So a word size read is always atomic, meaning if you're going to read 64 bits from memory or whatever, it's always atomic. You read 64 bits at a time in one shot. Okay, so that means a read of a single word cannot complete in the middle of a write to that word. Okay, so that means a write to that word blocks the read. The read always returns a word in a consistent state, either before or after the write completes, but never in the middle. Okay, cool. So basically, either you read the value, right, your word value, either you read your 64 bits before the write finishes it, or you read it after, like the CPU. If you requested some sort of 64-bit value to come back to you, right, you could have gotten the value either before the write had occurred or after. Okay, whether it's right or wrong, that doesn't matter. There's no guarantees that's right, so it could be wrong, but the fact is that you can never read a word, in this case a 64-bit value, in a state where your CPU is in the middle of writing to that same value, right? So yeah, So consequently, atomic read is usually just a macro returning the integer value of atomic t. So it's as simple as this. That's the implementation of atomic read. Just return the value of counter pointed by v. Okay. Atomicity versus ordering. The preceding discussion on atomic reading begs a discussion on the differences between atomicity and ordering. As discussed, a word size read always occurs atomically. It never interleaves with the write to the same word. The read always returns the word in a consistent state, perhaps before the write completes or perhaps after, but never during. For example, if an integer is initially 42 and then set to 365, a read on the integer always returns 42 or 365 and never some commingling of the two values. We call this atomicity. Your code, however, might have more stringent requirements than this. Perhaps you require that the read always occurs before the write. This type of requirement is not atomicity, but ordering. So yeah, don't confuse atomic meaning that you write or you read before write, or you always read after write. That's just ordering. The whole point of atomicity is that you're able to operate or do some sort of operation in a single uninterruptible step. That's all it is. Whether it's right or wrong, whether it fits what you wanted or expected, that's different. Okay, so when it comes to ordering of the operations, that's called ordering. Atomicity ensures that the instructions occur without interruption and that they complete either in their entirety or not at all. So reiterating what we just said. Ordering, on the other hand, ensures that the desired relative ordering of two or more instructions, even if they are to occur in separate threads of execution or even separate processor, is preserved. Okay? The atomic operations discussed in this section guarantee only atomicity. Ordering is enforced via barrier operations, which we discuss later in this chapter. Okay, so everything we've talked about is just how do we get operations to finish in a single, indivisible, uninterruptible step. Okay, we're not really concerned right now at this moment about the ordering of these operations to yield the result that we want. We're just caring about that atomicity part of it, the atomic part of it, sorry. Words. Okay. So in your code, it is usually preferred to choose atomic operations over more complicated locking mechanisms. On most architectures, one or two atomic operations incur less overhead and less cache line thrashing than a more complicated synchronization method. So if you can, prefer to use atomic operations to do things instead of like complicated like logic for locking. So as with any performance sensitive code, however, testing multiple approaches is always smart. Okay. So 64-bit atomic operations. With the rising prevalence of 64-bit architectures, well, this was written in 2010, so it's like now at this point 15 years ago. So it's 64-bit is the thing now. So it is no surprise that the Linux kernel developers augmented the 32-bit atomic T type with a 64-bit variant called atomic 64T. Okay, so that's a 64-bit version of atomic T. For portability, the size of atomic T cannot change between architectures. So atomic T is 32-bit even on 64-bit architectures. Okay, so even though atomic 64T is now a 64-bit integer, it still retains values that range from 0 or whatever to atomic T, or negative 2 to the 32 to, negative 2 to, no, sorry. Yes. Negative 2 to the 32 to 2 to the 31. I forgot how that works. -1 or something like that. Yeah. I don't know. Basically, from whatever negative 32 supports, 32-bit supports, to the positive that 32-bit supports. Okay. Instead, the atomic T type provides a 64-bit atomic integer that functions otherwise identical to its 32-bit brother. So it just reads at 64 bits, but the values are just 32 bits internally. Usage, so that means like the higher level 32 bits are like kind of just 0 in this case. Usage is exactly the same, except that the usable range of the integer is 64 rather than 32 bits. Nearly all the classic 32-bit atomic operations are implemented in 64-bit variants. They are prefixed with atomic 64 in lieu of atomic. Table 10.2 is a full listing of the standard operations. Some architectures implement more, but they are not portable. Okay, so they're not translatable to other architectures. As with atomic T, the atomic 64T type is just a simple wrapper around an integer, this time a long. Okay, so same thing as atomic T, except instead of volatile int, now we're doing volatile long. Okay, and the same, like the API is just like 64 with it. So not gonna read all that, but you would kind of just assume there's corresponding things. If you have an add, you have a sub, you have an inc, you have a dec, so on. Increment, decrement. Okay, so all 64-bit architectures provide atomic 64T and a family of arithmetic functions to operate on it. Most 32-bit architectures do not, however, support atomic 64T. x8632 is a notable exception. For portability between all Linux's supported architectures, developers should use the 32-bit atomic T type. The 64-bit atomic 64T is reserved for code that is both architecture specific and requires 64 bits. Okay, I don't think that's really relevant anymore, so we just assume. Okay, atomic bitwise operations. In addition to atomic integer operations, the kernel also provides a family of functions that operate at the bit level. So before we were operating on the integer level, the number level, right? Now we also have API or functions, or whatever you call it, that operate at the very fine-grained bit level. Okay, so the specific bits of an integer. So if you have 32 bits, it's one of those bits in those 32. Not surprisingly, they are architecture specific and defined in asm-bit-ops.h. Okay, so architecture specific. So different, like same API, but different implementations across different types of CPUs in this case. What might be surprising is that the bitwise functions operate on generic memory addresses. Huh? What might be surprising is that the bitwise functions operate on generic memory addresses. The arguments are a pointer and a bit number. Oh, okay. A pointer to that value, and then a bit number of where you want to mess around with in that value. Okay, so bit 0 is the least significant bit of the given address. On 32-bit machines, bit 31 is the most significant bit. So 0 to 31. And bit 32 is the least significant of the following word. Okay? So on the next, like, what they're saying is like, if you had like a 32-bit number, right? So you had like bit 0 here, and then let's say you had like, 1, 0, and it's just like 31 here, and then 32, right, is going to be the next number. So 60, I'm going to embarrass myself, 64. Yeah, right there. So this is number, A, this is number B, and so on. Okay, so there are no limitations on the bit number supplied, although most uses of the functions provide a word and consequently a bit number between 0 and 31 on 32-bit machines and 0 and 63 on 64-bit machines. Because the functions operate on a generic pointer, there is no equivalent of the atomic integer's atomic T type. Instead, you can work with a pointer to whatever data you want. Consider an example. So we have a word here, a 64-bit word, unsigned, meaning only positive numbers. So 0 to whatever, 2 to 64, something like that. Set bit. So we want to set 0th bit to whatever. Oh, okay. So yeah, set 0th bit. Uh, ah, okay, okay. Let's read this correctly. We want to set the bit at position 0 within whatever is pointed by word, which is going to be that 64-bit number. When we say set, I am assuming they mean to turn whatever that bit is at position 0 to be 1. Okay, so now for this call here, where it's 1 address, word, it's setting bit 1 for that specific word. Okay, clear bit is going to unset it, which is meaning to set it to 0. So now we're setting bit 1 of word to 0. Okay, now change bit is just going to toggle. So if it's 1, it becomes 0. If it's 0, it becomes 1. Okay. Okay. That's better. Okay, so the naming is kind of weird, but that's what it's trying to do. Okay, so test and set bit 0. So test and set bit 0 atomically sets bit to 0 and returns the previous value 0. Okay, so then if we change bit 0 in word, meaning that now it was 1 before, now it's 0. Okay, so we test and set the bit 0. So now from 0 to 1. Okay, we still return back the previous value, which is 0. So this returns 0, and then this will always be false. That's true. If the following is legal, you can mix atomic bit instructions with normal C. So word equals to 7 now. Okay. Sure. I think that was just a demonstration that it was legal. Okay. Okay. A listing of the standard atomic bit operations is in table 10.3. Okay, so same thing again. You have those tests and sets, clears, change. It's a smaller set of functions. So okay, so conveniently non-atomic versions of all the bitwise functions are also provided. So non-atomic versions of these are also provided. They behave identically to their atomic siblings, except they do not guarantee atomicity, and their names are prefixed with double underscores. For example, the non-atomic form of test bit is double underscore test bit. If you do not require atomicity, say for example because a lock already protects your data, these variants of the bitwise functions might be faster. So performance, if you're already in a state where you're in a critical region and everything's locked and everything, and you want to set bits and things like that, you can just use the non-atomic versions because safe. All right. Oh, interesting. What the heck is a non-atomic bit operation? On first glance, the concept of a non-atomic bit operation might not make any sense. Only a single bit is involved. Thus, there is no possibility of inconsistency. If one of the operations succeeds, what else could matter? Sure, ordering might be important, but we are talking about atomicity here. At the end of the day, if the bit has a value provided by any of the instructions, we should be good to go, right? Let's jump back to just what atomicity means. Atomicity requires that either instructions succeed in their entirety, uninterrupted, or instructions fail to execute at all. Therefore, if you issue 2 atomic bit operations, you expect the 2 operations to succeed. So one executes, then the next one. After both operations complete, the bit needs to have the value as specified by the second operation. Moreover, however, at some point in time prior to the final operation, the bit needs to hold the value as specified by the first operation. Okay? Put more generally, real atomicity requires that all intermediate states be correctly realized. So basically, the whole point is that if I were to do 2 operations, right? If after operation 1, I were to just check the value of what it is, it should be the value that I deemed it to have set or cleared. If I'm clearing a bit or I'm setting a bit in one operation, After that operation, I should expect that value to be true in terms of like what I wanted. Okay. But in the second operation, right, in this case, if I were to say something else to set it or clear it to a specific value, after that second operation, I should expect it to be consistent with what I had like specified in that second operation. Okay. Okay. So, for example, assume you issue two atomic bit operations. Initially set the bit and then clear the bit. So operation 1 is to set the bit. Operation 2 is to clear the bit. Without atomic operations, the bit might end up cleared, but it might never have been set. Okay? Without atomic operations, the bit might end up being cleared. It might never have been set. You don't know because no atomic operations. Anything can happen. The set operation could occur simultaneously with the clear operation and fail. The clear operation would succeed and the bit would emerge cleared as intended. With atomic operations, however, the set would actually occur. There would be a moment in time when a read would show the bit as set, and then the clear would execute, the bit would be 0. This behavior can be important, especially when ordering comes into play or when dealing with hardware registers. Okay? So there's a moment in time. So let's assume in a world where we have atomic operations now, right? So we set the bit and then we clear it. So what does this mean? The set would actually occur, okay? There would be a moment in time when the read would show the bit as set, okay? That means if we were to read at some point in time, that should be true. It's set. And then after we clear the bit on the second operation, right, then a read would actually show that bit to be 0. Okay. So the kernel also provides routines to find the first set or unset bit starting at a given address. So these are helpers to find the first set bit or unset bit. So find first bit, which is set, given some sort of pointer to it long. And again, I don't know what the size means. Let's see. But the other one, there's a 0, 1, 2. So both functions take a pointer as their first argument and the number of bits in total to search as their second. They return the bit number of the first set or the first unset bit respectively. If your code is searching only a word, the routines double underscore FFS and FFZ, which take a single parameter of the word in which to search, are optimal. What? Both functions take both functions take a pointer as their first argument and the number of bits in total to search. Okay, so this could go beyond a word. Okay, great. So this could be like 96 bits or something like that. So the first group of like 96 bits, you'll find the first bit that's set. Okay, makes sense. And if we only wanted to search for a word, let's say our 64 bits, then FFS and FFZ are the helpers that we need. Okay, so that's what size is for. It just tells you, like, the group of whatever bits. Okay, unlike the atomic integer operations, code typically has no choice whether to use the bitwise operations. They are only portable way to set a specific bit. The only question is whether to use the atomic or non-atomic variants. If your code is inherently safe from race conditions, you can just use the non-atomic versions, which might be faster depending on the architecture. Okay, I need some water. Just hold on. Alrighty. Okay. All right. Stay hydrated. Okay, spin locks. Okay, so now we're gonna get into like locking. So this is probably going to be the fun part now. So now we know like the atomic stuff that we have available. Like, I guess now how do we like use that to create locking mechanisms? Okay. Spin locks. Although it would be nice if every critical region consisted of code that did nothing more complicated than incrementing a variable, reality is much crueler. So yeah, you're not always just gonna be incrementing variables, right? As like a critical operations. You could be like, maybe like performing some sort of like database thing, or making some sort of request, and then using that results of those requests to, from another process to shape data. That's reality there. In real life, critical regions can span multiple functions. Yep, multiple function calls. For example, it is often the case that data must be removed from one structure, formatted, parsed, and added to another structure. That is pretty much real life. This entire operation must occur atomically. Yeah, so like you had to do all this stuff, but you had to make it atomic, meaning again, atomic does not mean one operate, like it doesn't mean like one line of code, right? That's not what it really means. Atomic operations means that this whole set of operations here, if it's atomic, means that all of them, as you're doing all these operations, you are indivisible and uninterruptible. Okay. So you cannot be preempted in this case. So it must not be possible for the other code to read from or write to either structure before the update is completed, because simple atomic operations are clearly incapable of providing the needed protections in such a complex scenario, meaning the atomic operations that we just learned in the previous section, they're not sufficient. A more general method of synchronization is needed. Locks. So we're gonna go one step up now in this thing, right? So like in terms of like the level of complexity, we had maybe something like that's ugly. We had something like atomic function, atomic T, right? Functions. Now we're going to have locks. Okay. So, the most common lock in the Linux kernel is a spin lock. A spin lock is a lock that can be held by at most one thread of execution. So, only one thread at a time can hold a spin lock. More reasons why it's called a spin lock, we'll soon find out. Okay, so if a thread of execution attempts to acquire a spin lock while it is already held, which is called contended, the thread busy loops, spins, waiting for the lock to be available. Okay, so this is a definition of a spin lock. Okay, if a thread of execution attempts to acquire a spin lock while the spin lock has already been held, meaning that it's already been taken by another thread, we call that contended. The thread busy loops, spins, waiting for the lock to become available. Very important, because up until now, like in chapter 9, we were talking about like how if a lock has already been acquired, a person's in the room, right? Another thread comes to try, or another person tries to access that room, but it's locked already because the person in that room has a lock. It's just the one that wants to access the room goes to sleep. Well, that's just assuming that we're just having a normal lock. A spin lock, on the other hand, the thread that, or the person that wants that lock will just continuously try to reacquire it, meaning that it doesn't go to sleep. It just like loops over and over again, just trying to try and get that lock. Okay, so there are reasons to do this. And I think the book is gonna say it. So yeah, you don't go to sleep. You just kind of busy loop. You just stay there, like checking over again. That's performance. Like, it wastes a lot of CPU cycles, causes your CPU to work because for that specific thread. But again, reasons. If the lock is not contended, meaning that it's free to be grabbed, the thread can immediately acquire the lock and continue going into that critical region of code to do stuff, right? The spinning prevents more than one thread of execution from entering the critical region at any time. The same lock can be used in multiple locations, so all access to a given data structure, for example, can be protected and synchronized. Okay, so that lock, you can just pass that around and use that. Remember, like, these locks are objects, so they're just like variables. So going back to the door and key analogy from the last chapter, spin locks are akin to sitting outside the door waiting for the fellow inside to come out and hand you a key. If you reach the door and no one is inside, you can grab the key and enter the room. Okay? Okay. If you reach the door and someone is currently inside, you must wait outside for the key, effectively checking for its presence repeatedly. When the room is vacated, you can grab the key and go inside. Thanks to the key, read spin lock, only one person, read threat of execution, is allowed inside the room. Read critical region at the same time. Okay. So let's do this. Okay. The key is a spin lock, the person is a thread, and the room is the critical region. Okay. The fact that a contended spin lock causes threads to spin, essentially wasting processor time while waiting for the lock to become available, is salient. This behavior is the point of the spin lock. It is not wise to hold a spin lock for a long time. This is the nature of the spin lock, a lightweight single holder lock that should be held for short durations. Okay? Alright, sorry, gotta read that again to explain. The fact that a contended spin lock causes threads to spin, essentially wasting processor time. So it's just eating up cycles. Think about like a loop, right? Just like spinning, doing nothing. Because it's just waiting for the lock. Like hopefully that lock is now available and I can just grab it as soon as possible. This behavior is the point of the spin lock. It is not wise to hold a spin lock for a long time because you're causing a bunch of threads that want that spin lock, right, to just spin and wait and busy loop, right? So this is the nature of spin lock, a lightweight single holder lock that should be held for short durations. So that means if you are the person that is grabbing that spin lock, you are responsible for not ruining the entire world by making them all wait for you in this busy looping fashion. You get that lock, you do what you need to do, and get out quickly. So that's the whole point of a spin lock. It's for operations that are so short, like critical regions that are really short, for just really quick things, and then just make that lock available for anybody else wanting to come. Okay? So an alternative behavior when the lock is contended is to put the current thread to sleep, okay, and wake it up when it comes available. So that's like the other way of locking. Then the processor can go off and execute other code. This incurs a bit of overhead, most notably the two context switches required to switch out of and back into the blocking thread. So yes, the one thing that spin locks like have benefit, like there's a benefit to spin locks in that if you know that the critical region is really short, you don't have to have thread sleep, wasting that context switch time. Like you have the context switch, right? And when you context switch, there's a performance implication on that. When you context switch, you end up clearing pretty much like in your L1 caches and things like that in preparation for the next thread to execute, and all that is, there's a cost to it. So for really small simple things, you don't want to do that. You want to just let that thread like kind of wait in the busy loop really fast. So and it's certainly a lot more code than the handful of lines used to implement a spin lock. Therefore, it is wise to hold spin locks for less than the duration of two context switches, because most of us have better things to do than measure context switches. Try to hold the lock for as little time as possible. Later in this chapter, we discuss semaphores, which provide a lock that makes the waiting thread sleep rather than spin when contended. Okay, so now we finally have a term for the type of lock that actually allows the thread to sleep waiting for it, right? That's a semaphore. And whereas the one where you have to, when you grab the lock, you're causing all the threads to spin and just like kind of waste cycles in the loop, just checking. That's called the spin lock. So the semaphore, sleep, spin locks, busy loop. Okay, so spin lock methods. Spin locks are architecture dependent and implemented in assembly. The architecture dependent code, meaning that it's CPU architecture, like dependent related. Code is defined in ASM spinlock.h. The actual usable interfaces are defined in Linux spinlock.h. The basic use of a spin lock is define spin lock, Mr. Lock. Just kidding, MR lock. MR lock. So the actual user interface are defined in here. How you actually, make a spin lock object is through this define spin lock macro. You pass in the name of the lock you want to create. This is going to just get replaced as like a variable declaration. So now your MR lock, or I like to say Mr. Lock variable, is going to be defined, and you can use that as your spin lock. And then here you go, you use the spin lock function call right here with the pointer to Mr. Lock that allows you to just grab that lock. And then from here on, anybody wanting Mr. Lock has to busy wait. Okay, you do your little thing in here, like literally little, like really fast code. And then you unlock Mr. Lock. Now you're making Mr. Lock being available for everybody to use later on. Okay, so spin unlock, spin lock, and then define spin lock is pretty much the API. And I think here is like, all right, so the lock can be held simultaneously by at most only one thread of execution. Consequently, only one thread is allowed in the critical region at a time. This provides the needed protection from concurrency on multiprocessing machines. On uniprocessor machines, the lock compiles away and do not exist. They simply act as markers to disable and enable kernel preemption. If the kernel preempt is off, the locks compile away entirely. I don't think we need to worry about that. I think we should assume that it should always be there, so we can think of it that way. Yeah. So warning, spin locks are not recursive. Unlike spin lock implementations in other operating systems and threading libraries, the Linux kernel spin locks are not recursive. This means that if you attempt to acquire a lock you already hold, you will spin, waiting for yourself to release the lock. Okay, so you can actually in a silly way, deadlock yourself by acquiring the lock twice, because it's not aware that if you try to acquire the lock again when you're already holding the lock, let's say another function call, right? You get the lock and then you call another function that happens to have that same lock object, and you try to acquire it again. But since you already, as a thread, already have the lock, right? You're going to just busy waiting for that thread, which is you, to release that lock. But since you're too busy waiting, you never make any progress to release it. So be careful. But because you are already busy spinning, yeah, see, you're too busy spinning. You'll never release the lock and you will deadlock. Be careful. Spin locks can be used in interrupt handlers where semaphores cannot be used because they sleep. Okay, so spin locks are used in interrupt handlers. Semaphores cannot be used in interrupt handlers because semaphores causes threads to sleep, whereas spin locks don't. So if you need to lock in interrupt handlers, spin locks can be used. So if a lock is used in an interrupt handler, you must also disable local interrupts. Okay, interrupt requests on the current processor before obtaining the lock. Otherwise, it is possible for an interrupt handler to interrupt kernel code while the lock is held and attempt to reacquire the lock. So yeah, this is like when you're doing things like soft IRQs and tasklets. It makes sense that you need to disable the interrupts because you're in interrupt context in this case. So the interrupt handler spins, waiting for the lock to become available. The lock holder, however, does not run until the interrupt handler completes. This is an example of a double acquired deadlock discussed in the previous chapter. Note that you need to disable interrupts only on the current CPU, the current processor core. If an interrupt occurs on a different core, right, different processor, and it spins on the same lock, it does not prevent the lock holder, which is on a different processor, from eventually releasing the lock. So the kernel provides an interface that conveniently disables interrupts and acquires the lock. The usage is basically you define the spin lock, Mr. Lock, all right, and then you do spin lock RQ save. So what that allows you to do is, given these two arguments, remember flags here from our interrupts disabling code, you can acquire the spin lock and also disable local interrupts at the same time. So when we say local interrupts, we disable interrupts only on the current processor. Then we perform our critical region code, and then we unlock and restore interrupts processing all in one shot in one function call. So this is, I guess, a common pattern enough that there's helpers for it. Okay. Actually, before we keep going, let's actually find like a use of define spin lock and see how that's used in the code. So if we were to go here into our source code and just search for define spin lock, I'm sure that there is stuff here. Let's see. Let's do sound. Yeah, let's do sound core. Get some sort of sound driver or an NFS cache. Let's do sound. Okay, so we have defined spin lock here, and the lock right here is called the sound loader lock, right? So let's find occurrence of sound loader lock and see what happens right here. So this static sound insert unit, whatever this inline function is acquiring a spin lock called sound loader lock, which we had defined it up earlier. So if we were to go back here, this defined spin lock here allows us to, make that spin lock. Oops, where is it? Right here. Yeah, and then we can use it to do this critical region code here, right? And then unlock it immediately. So notice how this critical region is only one function call. So it's basically maybe it's going to be what sound insert unit. Yeah, it's probably going to do something really quick here in this case. So details, we don't really care. We just want to see the usage of define spin lock. So that's how we use it. Okay. Okay, so so the routine spin lock RQ saves the current state of interrupts, disables them locally, and then obtains the given lock. All right. Conversely, spin unlock RQ restore unlocks the given lock and returns interrupts to their previous state. This way, if interrupts were initially disabled, your code would not erroneously enable them, but instead keep them disabled. Note that the flags variable is seemingly passed by value. Okay, right here. This is because the lock routines are implemented partially as macros. So internally, this will probably just get the pointer to it. So these are just macros. All right. On uniprocessor systems, previous example must still disable interrupts to prevent an interrupt handler from accessing the shared data, but the lock mechanism is compiled away. The lock and unlock also disable and enable kernel preemption respectively. So what do I lock? It is important that each lock is clearly associated with what it is locking. More important, you should protect data and not code. So always think about protecting data and not code. Despite the examples in this chapter explaining the importance of protecting the critical sections, it is the actual data inside that needs protection and not the code. It just so happens that because when you operate on data, you need code, right? So that's the reason it looks like you're protecting code, but it's really you're protecting the data from these operations, modifying it. Okay, so here's a big fat rule. Locks that simply wrap code regions are hard to understand and prone to race conditions. Lock data, not code. Okay. Rather than lock code, always associate your shared data with a specific lock. So always create like these individual locks. For example, the struct foo is locked by foo lock. So don't like try to create like a global lock or something like that. Just create like locks specific to the data that you want to protect. Whenever you access shared data, make sure it is safe. Most likely this means obtaining the appropriate lock before manipulating the data and releasing the lock when finished. If you always know before the fact that interrupts are initially enabled, there is no need to restore their previous state. You can unconditionally enable them on unlock. Okay? In those cases, spin lock IRQ and spin unlock IRQ are optimal. Oh, okay. Wait, if you always know before the fact that interrupts are initially enabled, there's no need to restore to the previous state. So if you always know that interrupts are always going to be enabled, okay, you can just do this. Okay. As a kernel grows in size and complexity, it is increasingly hard to ensure that interrupts are always enabled in any given code path of the kernel. Use of spin lock IRQ therefore is not recommended. Okay. So don't do this. Okay. Okay. All right. So they're like, if you know it's enabled, then do this, but you probably should not do it at all. Okay. So, all right. If you do use it, you better be positive that interrupts were originally on, or people will be upset when they expect interrupts to be off, but find them on. So one more time, don't do this, I guess. Okay. Debugging spin locks. The configure option config debug spin lock enables a handful of debugging checks in the spin lock code. For example, with this option, the spin lock code checks for the use of uninitialized spin locks and unlocking a lock that has not yet locked. Am I just as confused reading that? Okay, so we have a configuration option called config debug spin lock. And it allows us to have like debugging features, right? To check spin lock code. Okay. All right. So far, so good. For example, with this option, the spin lock code checks for the use of uninitialized spin locks. Okay, so if you're going to use a spin lock where we didn't actually do the whole define spin lock thing, right? It checks for that. If you're trying to use a spin lock that didn't use this call, I don't know why it's so ugly here, but yeah. Okay. Or you're trying to unlock a lock that's not yet locked. So it's probably like linting or something. When testing your code, you should always run with the spin lock debugging enabled. Okay, cool. For additional debugging of lock life cycles, enable config debug lock alloc. Okay. Other spin lock methods. You can use the method spin lock init to initialize a dynamically created spin lock, a spin lock t that you do not have a direct reference to, or just a pointer. The method spin try lock attempts to obtain the given spin lock. If the lock is contented, rather than spin and wait for the lock to be released, the function immediately returns 0. Okay, so you can use the method spin lock init to initialize a dynamically created spin lock. So basically, spin lock init is kind of like the dynamic version of this. Okay, this defines spin lock you have to create in code and compile. But suppose you don't really know where you're gonna actually define the spin lock yet, specific ways, you can just create one dynamically on the fly with this helper function. It will return you back with a new spin lock object. This one is like you already know the variable name you want, you already know where you need to lock, so good to know. Okay, the method spin try lock attempts to obtain the given spin lock. So basically, spin try lock takes in an argument here with a spin lock. So if the lock is contented, meaning that it's already been acquired, rather than spin and wait for the lock to be released, the function immediately returns 0. So spin try lock is not going to cause that busy waiting. Okay, so it's just kind of checking to see if it's contented, and the value here is going to be 0 if it's already been acquired by somebody else. Now, if you succeed in obtaining a lock, meaning that if the lock that you passed in hasn't been acquired yet, spin try lock will just basically acquire the lock for you and also return non-zero. So it does those two things at once. And then if it's already been contended, it just returns 0, but you don't busy wait. Okay. So similarly, spin is lock returns non-zero if the given lock is currently acquired. Otherwise, it just returns 0. So these are just helpful for checking the state of a spin lock. In neither case does spin is lock actually obtaining the lock. Okay, spin is lock. So spin is lock does not obtain the lock. It just checks to see. Okay, so if we look at more detail here, right here. So spin try lock tries to acquire a given lock. If unavailable, returns non-zero. Oh, whoa. Okay, so that's weird. I think I found some error. If the lock is contended, rather than spin and wait for the lock to be released, the function immediately returns 0. So that's it fails, right? Like it isn't able to acquire the lock. It's unavailable. So it returns 0. And if it succeeds, it returns non-zero. But here it says tries to acquire the given lock. If it is unavailable, returns non-zero. So there's an error here, I think. Okay. How about let's look at the implementation. So spin try lock. Okay. Can we figure out where that might be? Spin lock.c. Okay. Spin lock.c. Lock contended is there sort of int raw spin try lock. Okay, so is it called raw spin try lock? I think it's double under, so maybe it's an H. So redo spin lock.h. Spin try lock. Okay. Arch try spin try lock return. Okay, so I think that is actually architecture specific. Yeah, whatever. Okay, I'm not gonna look too hard into that, but I guess we can just find out in our code when we do code. So okay, spin locks and bottom halves. As discussed in chapter 8, bottom halves and deferring work, certain locking precautions must be taken when trying to work with bottom halves. The function spin lock bh obtains the given lock and disables all bottom halves. Okay, the function spin unlock bh performs the inverse. Okay, because a bottom half might preempt the process context code. If data is shared between a bottom half process context, you must protect the data in process context with both a lock and disabling of the bottom halves. Likewise, because an interrupt handler might preempt a bottom half, if data is shared between an interrupt handler and a bottom half, you must obtain the appropriate lock and disable interrupts. Okay. Wait, where's... Okay. Cool. So recall that two tasklets of the same type do not ever run simultaneously. Thus, there is no need to protect data used only with a single type of tasklet. If the data is shared between two different tasklets, however, you must obtain a normal spin lock before accessing the data in the bottom half. You do not need to disable bottom halves because a tasklet never preempts another running tasklet on the same processor. With soft IRQs, regardless of whether it is the same soft IRQ type, if data is shared by soft IRQs, it must be protected with a lock. Okay, so that's where spin locks come in. Recall that soft IRQs, even two of the same type, might simultaneously run on multiple processors in the system. A soft IRQ never preempts another soft IRQ running on the same processor. However, so disabling bottom halves is not needed. Okay. So you have to use a lock, but you don't need to disable the bottom halves on that same processor. Sure. Okay. This is running long, but I am going to pause for now and continue later. See you in a bit.